So I will say something about a section that we skipped. So I thought we could do it if we have time. We don't have too much time. I will just briefly mention it. And this is about, okay, this is an optional section. Okay, optional. And it's about section 4.9. Let me. Okay. Anyway, so this is about, this is 4.9, the rank of a matrix, okay? So this is something that we didn't talk about. The rank of a matrix. This is an optional section. I will just talk just 5 minutes about this, so that at least you see the idea. So what is the rank of a matrix? So suppose we have a matrix like, there's something wrong with my. So let's take an arbitrary matrix, okay? It doesn't matter. So 1, 2, 5, 3, 1, 4. Okay, so the question is, how many independent rows are there in this matrix? So number of independent rows. Independent rows. So it turns out that the number of independent rows is equal to number of independent. Did I start recording the lecture? Let me see. Yes. Kalemim yazmıyor arkadaşlar artık. Elimle şöyle yazmaya çalışacağım. Number of. Elde hiç olmuyor. Okay, number of independent columns. Independent columns. So for example, for this example, we have 2 rows. So these 2 rows are independent, right? Because they are not multiples of each other. So both are 2, okay? For this example. And this common number is called the rank of a matrix, rank of a matrix. So if you have, I don't know, like a matrix, very large matrix, which has, I don't know, 80 rows and 15 columns, then it turns out that the number, so the rank of this matrix can be at most 15, right? Because you have 15 columns, so number of independent columns can be at most 15, which means the number of independent rows can also be 15. So most of the rows will be linearly, they will be linearly dependent. There will be at most 15 independent rows. So that's it. And there's something called, okay, so let's remember something. So if we have A times X, so suppose A is a M by N matrix, and so if you remember, the solution set of this equation is a space. Solution set of this equation is something called null space of A. Null space of A, okay? So this is a subspace of Rn, okay? Subspace of Rn. Now here's something called fundamental. So if you remember, there was a fundamental theorem of calculus, right? Fundamental theorem of calculus said something very important about calculus, which is basically integration and differentiation are inverse operations of each other. So there is some kind of fundamental theorem of linear algebra that I didn't mention. Okay, so it's fundamental, but I didn't mention because we couldn't use it. Okay, so maybe you will see some applications of it in the future. So fundamental theorem of linear algebra says this. So fundamental theorem of algebra says rank of a matrix, rank of A, plus dimension of null space of A, dimension of null space of A equals the number of basically, so this number n, okay, so the number of columns of A. Okay, so this is like a theoretical thing that we didn't use, we don't need to use in our discussion, but it's called fundamental theorem of linear algebra. So at least I thought that I should mention this. So for example, if we go back to this example, so we said that the rank of this matrix is 2. So it turns out that the dimension of null space of this matrix must be 1. Okay, so what does it mean? It means that for this example, this equation AX equals 0 must have one linearly independent solution. Okay, so there will be infinitely many solutions, and that those infinitely many solutions will be generated by one vector. Okay, that's it. Yeah, so even if we don't find, so for example, for this one, so let's write this as an example. So let's copy this matrix. Kendime yeni bir kalem sipariş verdim. Kalem artık yazmıyor arkadaşlar. Ucu gitti. Okay, so let's copy this. Kızım sağ olsun ucunu yediği için. Okay, so if A is this, so we said that the rank is 2, which means, so what does this mean? This means dimension of null space. So we gave a special name to this expression, right? So the special name is nullity. So we said this is called nullity, which means nullity must be 1 because number of columns is 3. Okay, so that's by fundamental theorem of linear algebra, fundamental theorem of linear algebra, FTLA. It says nullity must be 1. So what does this imply? This implies that AX equals 0. So the homogeneous equation has one linearly independent solution, exactly one linearly independent solution. That's good to know, right? That's something good to know. So we can do this without solving the equation. So it comes from the fundamental theorem of linear algebra. Okay, so that's so I can talk more about it, but we don't have time. So I will try to solve some exercises, some problems for the midterm. Let me know if you have any questions about this discussion. So, and I will also put this whole thing in the website in case you want to study from here as well, okay? So this material is for the final exam, not for the midterm exam. Okay, but I will put it in the our website. Okay, any questions? No. Okay, let me stop the sharing for a moment because I need to do something from here. My Dropbox. Sorusu olan varsa sorabilir arkadaşlar şu sessizlikte. Buraya koymuş. Bunu yapmasını istemedim. Okay, so let me start the share again. No questions, right? Okay. Okay, so here are some exercises for the week for that we will talk about this week. So these are from the first chapter, second chapter, and the third chapter. Okay, let's look at some of these exercises. So let's look at this one, number 37 from chapter 1.4. I also sent you an email, okay, about the possible suggested midterm exercises. What are eigenvectors good for? And what are they geometrically? So I talked about a little bit. They are good for a lot of things, so I cannot explain all the things that they are good for. There's a whole chapter about it. And one thing that I mostly use is for solving differential equations. Okay, so differential equations, you didn't take it yet, but all the laws of physics and like general laws of biology and all those stuffs can be expressed as differential equations. So if you try to solve them, they come up naturally. So it's good to obtain to understand what eigenvectors are. Geometrically, an eigenvector is, so there are two different cases. So one is, so we are looking for directions which the matrix leaves invariant. What does it mean? So if we want to find a direction such that when I apply this vector by A, I want it to lie on the same line, right? So this is, so if this is X, so if this red one is X, eigenvectors are such x's for which ax and x lie on the same direction if eigenvalues are real. So if eigenvalues are complex, it also corresponds to some kind of rotation. Okay, so we want this invariance to be in like the complex plane. It's little bit more difficult to explain, but we're basically looking for directions for which x and ax lie on the same line. So that's what at least what real eigenvalues and real eigenvectors are. Yeah, that's all I'm gonna say for now. Okay, so you can also look at the Wikipedia page. Okay, so there are some more discussions in the Wikipedia page about eigenvalues and eigenvectors. So let's go back to these problems. Okay, so we have a linear system, right? So A, C and A and C are matrices. X is a vector. Vectors are also matrices, doesn't matter. So we are not given A and C, but we are given the inverses, okay? And we know the right-hand side, so we're trying to find the solution. How do we do that? So one way of doing is, so difficult way of doing is, try to find A and try to find C, and then try to solve the system using row echelon form. Okay? But that's the difficult way. Easy way is, so if you have this equation AC times, no, A capital C, right? A times C X equals B. So what do you do here? So what you do is, since you know this A inverse matrix, you can multiply both sides with A inverse, okay? So if you do that, so you have to be careful about the direction you multiply. Okay, so A inverse and A, so if you multiply, they will cancel each other. They will give the identity matrix. This product is identity matrix. So this means C times X is A inverse times B. And what is the, so B is also a vector. Next thing is, we can repeat this with C inverse, multiply by C inverse from left, okay? So we will get C inverse, A inverse times B. And this guy is also identity matrix. So we obtained the vector X. Okay, so one thing people always do mistakes. So maybe half of the class does this mistake. So when you're multiplying matrices, you have to be careful about the direction. So here, I'm multiplying A inverse from left, right? So from here. When I do that, I have to multiply A inverse by here. But a lot of people, they multiply A inverse from left here and they multiply from right here. That doesn't work. Also, A inverse and A doesn't cancel if A inverse is here, okay? So A times C times X times A inverse, this is not even defined, okay? This is not even defined. So when you're multiplying, you have to make sure that the product is defined and you multiply both sides of the equation from left, because matrix product is not commutative. You cannot change the order. That's very important. Okay, that's the reason you have to multiply from the same side. So here I'm multiplying from left and I'm multiplying from left. So once I get this, I have to multiply from left by C inverse to cancel this C. Okay, so this is very easy, but a lot of people make mistakes and that really frustrates me. So when I see such things, I'm very frustrated about it. So please be careful about it. So once you compute this, you get this. Now we can compute the result, right? So what you do is you first multiply A inverse by B. So let's do it. So A inverse times B. What is A inverse times B? Let me write C inverse also here. So this is C inverse. A inverse is 2, 1, minus 1, 1. What is B? B is 2, no, 2 and 3. So we have C inverse here. If I take this product, 2 times 2 is 2, 1 times 3 is 3, 2 times 2 is 4, I'm sorry, 7, and 7 and 1. Now if I make this C times 7, 1, I get 14, 15, and I get 7 and 2 is 9, 15 and 9, okay? So this is the solution. Oh, I didn't write the question, right? The question is find X. The question was find x, because all the other things are known. So there's only x missing. So we're trying to find x. Okay, so find all 2 by 2 matrices of this form, okay, and these are real numbers, A, B, C, such that if I take the product with itself, it will give me the identity matrix, okay? So A, 0, B, C times A, B, 0, C must give me identity matrix 1, 0, 0, 1. Okay, so if I do that, what do I get? So I get A squared here. Then I get AB plus BC. From this part, I get 0. And from this part, I get C squared. So this is same as 1, 0, 0, 1. Okay, so from here, I get A must be plus or minus 1. And C must be plus or minus 1. That gives me B, A plus C must be 0, right? Because these two, let me show it. So this must be equal to 0. So A plus C is 0, which means A is negative C. Okay, so that gives me all possible, or either B is 0 or A equals minus C. Okay, so yes, that's the general solution. Okay, I don't want to write everything down. So the general, all possible such matrices must satisfy this. A is either plus or minus 1, C is either plus or minus 1, and either B is 0 or A is minus C. Okay, that's the general solution. Okay, so yeah, I don't want to write too much about it. Okay. Show that the product of two by two skew-symmetric matrices is diagonal. Okay, so how do we do this? So for this, we have to recall what skew-symmetric matrix is. So skew-symmetric matrices are those matrices for which the transpose equals the minus the matrix itself, right? A transpose equals minus A. Okay, so what does this mean? So if I take 2 by 2 matrices, A, B, C, D, this is A, and if it equals, so A transpose equals minus A means what? It means if I take the transpose, I get A, B, C, D, right? And this equals minus the matrix itself, which means A, B, C, and D. Okay, so what does this mean? This means A is equal to minus A, so that A is 0, and D equals minus D, so that D is 0, and C equals minus B, and the last equation is B equals minus C. Okay, so this means 2 by 2 skew-symmetric matrices must satisfy this. So A must be 0, D must be 0, and this guy should be of the form B and minus B. Okay, so any 2 by 2 skew-symmetric matrix is like this. So if I take the product of two 2 by 2 skew-symmetric matrix, so A is this, and suppose I get another matrix which is 0, C, minus C, and 0. Okay, so these are two arbitrary skew-symmetric matrices. If I take the product A times B, what do I get? I get minus BC, right? And then 0, here this is also 0, and this will become minus BC. So you see this matrix is a diagonal matrix because all the entries are on the main diagonal, okay? Non-zero entries, possible non-zero entries. Is this true for n by n skew-symmetric matrices where n greater than 2? Okay, I won't do this part. You can try to see it, okay? So I suggest you work with 3 by 3 case to get the understanding, okay? How it goes. So another problem, prove that if the trace of this A transpose times A is 0, then the matrix must be 0. So what is trace? Okay, so I think, so let's just do this for 2 by 2 case, okay? So trace of a 2 by 2 matrix is what? It's the sum of entries on the diagonal. So if the trace of, so what is A transpose? A transpose will be A, B, C, D times, what is this guy? A, B, C, D, right? So if I take this transpose, if I take the trace of this product, what do I get? I get trace A square, so A square plus C square. And these guys don't matter because when I'm computing trace, these won't come into the picture. And the last entry is B square plus D square. Oops. So if I take the trace, I'm adding the entries on the diagonal. So this gives me, okay, if this is 0, what does it mean? This means all these entries must be 0. Which means the matrix must be 0, right? So if all the entries of the matrix is 0, then the matrix must be 0. Okay, I did this example for 2 by 2 case, and you can check it for 3 by 3 case, for example. If you can do it, try to do it for n by n case, okay? Okay. Any questions? Okay, these are some of the things that you should know from chapter 1. Let's go to chapter 2. Okay, you know how the midterm works, right? I think I will upload it in the morning, and then you will have like 4 hours or 4 or 5 hours to solve it. And then you will scan and send it using the system. I think the department will send you an email about it. Okay, so this is from section 2.2. So this says find a 2 by 1 matrix X, which means a vector, right? Because 2 by 1 matrix is a column vector with entries not all 0 such that this equation holds. Okay, basically what it's asking here is find the eigenvector corresponding to the eigenvalue 3. Okay, so this exactly means finding an eigenvector. So how do we do it? We have seen this last week, right? So what we do is 2, 1, 1, 2 times, let's represent the x vector by x1 and x2. So this is 3 times x1 and x2. This gives us what? This gives us the right-hand side is 2x1 plus x2. Right-hand side is 3x1. And for the second line, x1 plus 2x2 equals 3x2. Okay. So if I take this to other side, I get minus x1 plus x2 is 0. And for this one, I will get minus 2x2, x1 plus 2x2 equals 0. Okay, so you see these two equations are not independent. So the second equation is basically a multiple of the first one, so it is redundant. And this is expected because otherwise, if both of these equations are independent, then the only solution we would get is x1 equals x2 equals 0. So we must have these two equations dependent. Otherwise, there will be only trivial solution, and we cannot find a vector whose entries are not all 0. So this means x1 equals x2, and x2 is free. So I give it the name R. Okay, so from here I can, so any solution of this form is a solution, right? Because if I choose x2 equals R, then if this is R, this should be also be R. Okay, so this holds for any R. So for example, as an example, we can choose the vector 1, 1 or 5, 5 or 7, 7, anyone works. Any questions? Okay, probably I have solved some of these questions, but I don't remember. İkinci denklemde bir hata var mı? Bir hata mı var hocam? Nasıl bir hata olsun? Bir hata yok. İkinci denklem normal. Yani ikinci denklem birinci denklemin bir katı. Tamam mı? Eğer katı olmasaydı, bu iki denklem birbiriyle bağımsız o denklemler olsaydı tek bir çözüm bulabilecektik. O da 0-0 çözümü. Yani bu şekilde birbirine bağlı olması lazım ki bu iki denklemin sıfırdan farklı bir çözüm bulabilelim. Onu demek istedim. Bir hata yok denklemlerde. Okay. So in the following linear system, determine all values of A for which the resulting linear system has no solution, unique solution, infinitely many solutions. So let's look at it. Okay, so probably I have solved this. I don't remember. So how does this work? So we first of all we write this 1, 1. So let me remember 1, 1, 1. I'm writing the coefficients of the system 1, 2, 1. And for z, I get -1 plus 1. -1 plus 1. What is this? 1 a square. Okay, so this is the augmented matrix. So I'm writing the right-hand side here, 2, 3, and a. Okay, so okay, so what do we do? So we're trying to use row echelon form, right? Row echelon form. So how do we use row echelon form? So we play with so we first choose the first leading one. The first leading one is this one, okay? So using that, I'm eliminating entries from the first column. So making this one and this one 0, okay? So if you do that, what is happening? So I am multiplying the first row by -1 and adding it to the second row and replacing second row by this one, okay? And similarly for the third row. If I do these two operations, what do I get? I get 1, 0, 0, and this becomes 1. So what did I do? So I multiply this row by -1 and add it to the second row. So this is 1, and this is 2, right? So this is 2. This will become 1. And same thing here. This will become 0. So this will become a squared minus 4, and this will become a minus 2. Okay, so this is in now row echelon form, right? This is in row echelon form because I mean row echelon form if this guy is either 1 or 0. Okay, so let's see. Now, what are the possibilities here? So one possibility here is if this guy is 0, but this guy is not 0, okay, if a squared minus 4 is 0 and a minus 2 is not 0, then what does it mean? This means 0x plus 0y plus 0z equals something non-zero, which is not possible. In this case, there are no solutions. So in this case, the system has no solutions, right? So when is this case possible? If a squared minus 4 is 0 and a minus 2 is not 0. This is only possible if a is, so this is possible if a is 2 or minus 2. And this is possible if a is not 2. So the only case is if a is minus 2, then you see this guy is 0, but this guy is not 0. So in this case, there are no solutions. Okay. Any questions here? No. Okay, this is the first case, right? So no solution. If a is minus 2, there are no solutions. Let me write here. If a is minus 2, then there are no solutions. So when is there a unique solution? When is there a unique solution? So unique solution happens if this guy is not 0. If this is not 0, if this is, for example, 8, then I can divide the last line to 8, okay? So this will give me, so I will divide by 8. This will give me the solution for z. So z equals this guy minus a squared minus 4. Once I solve z, I put it back here and I solve for y. Once I get y, I get y and z and I can solve for x. So if this is not 0, then the system will have unique solution. Okay, so for part B, if a squared minus 4 is not 0, then there is a unique solution. Okay. So this means if a is not 2 or minus 2. If a is not 2 or minus 2, then there will be a unique solution. And for part C, when is there an infinitely many solution? When are there infinitely many solutions? So for infinitely many solutions, this guy must be 0. Okay, so we said that otherwise there will be infinitely many solutions. So if this is 0, but if this is not 0, we talked about it, there are no solutions. If both are 0, if both this one and this one are 0, then the last equation is automatically satisfied. The system is consistent. But now we have only 2 leading ones, and the last column doesn't have a leading one. If you remember this was the case for infinitely many solutions because we can choose the last variable free. Okay, so in this case, if a square minus 4 is 0 and a minus 2 is 0, then we have infinitely many solutions. Okay, when is this possible? This is possible if a is 2. Okay, so a is if infinite, so if a is 2. Okay, this covers all the cases. So if a is minus 2, we have no solution. If a is 2, there are infinitely many solutions. And if a is none of these, oh, I wrote the same thing twice, right? So this one of them should be minus 2. If a is not 2 or minus 2, then there will be a unique solution. Any questions?